to introduce our speaker, Professor Andres Arazi, who is going to talk to us about the 20 UD Tandem Accelerator facility of Argentina. Professor Arazi is a well-experienced experimentalist. He graduated in physics from the University of Buenos Aires. He did his PhD in the area of accelerator mass spectroscopy, studying 25 magnesium P-gamma reaction to populate 26 aluminium at astrophysical energies in the University of Munich Technical University and the University of Vienna. He has published number of original research articles and presented at various national or international platforms. He is a researcher at the Atomic Energy National Commission of Argentina and also an independent researcher at the National Scientific and Technical Research Council of Argentina. He is having active collaborations with Brazil and Spain in nuclear reactions and with Australia in AMS. From my communication with him so far, I can tell you he is a kind personality with an open mind, and we are very lucky to have him here with us. So feel free to discuss with him.
Okay, thank you very much, Bhumika, and also thank you to Vijay who proposed me for this talk. It's a great pleasure and honor to be able to present to you what activities are being done in our facility. I'm going to speak on behalf of several groups, just presenting some research, applied research, and then try to focus on the basic research on nuclear reactions. So this facility, this accelerator called Tandem, stands from Tandem of Argentina, was purchased from National Electrostatic Corporation in the early 80s. It was constructed, the facility, in up to the 85. And since then, it had been operating for basic and applied research. So in this talk, I will describe the facility very briefly, make a very quick overview of the applied research, which includes accelerator mass spectrometry, PIXE and micro-PIXE to environmental studies, and radiation damage on solar cells and also on electronic devices. And then I will try to focus in the basic research we are doing for nuclear reaction, try to describe the detection system, which includes silicon detector arrays or telescopes or double-sided silicon strip detectors, and describe what we have been doing, which is offline detection of gamma rays, and well, try to tell you about recent results and what we are doing right now. So this is a nice picture of the tower. It's practically 70 meters high. We have a fancy conference room on the top. Here's the ion source, and here at the bottom is, of course, the experimental rooms. This is our ion source and pre-acceleration. We have a 40 samples pattern negative ion source, which is very useful for AMS, for accelerator mass spectrometry, in which you must change the sample very frequently. You have, of course, a 90-degree magnet and a recently installed 360 kilovolt pre-accelerator power supply, which provides the pre-accelerator to be injected into the main accelerator. This is the nice picture of this accelerator, which is 35 meters high, has 20 units in each side, in high energy and in low energy sides, have 4 charge chains, which run from the column top up down to the terminal. An issue with this accelerator is that it's designed for SF6, for hexafluoride, but most of this gas has been lost along years, so it has been replaced or refilled with nitrogen and carbon dioxide, and a very small amount of SF6 is left. And we are trying now to buy in order to replace or to increase the amount of FX6 which is in the tank. And nowadays we can achieve 10 megavolts in the terminal, which gives us 5 MeV per nucleon, which is quite good for many research and application as well. This is our analyzing magnet, which is double focusing, and a particularity of our facility that we don't have a switching magnet. Rather, this magnet rotates mechanically to fit each beam line, and that saves or have saved a lot of money, because a switching magnet is expensive, but also saves quite a lot of space. So just look how is the layout of the facility. Here is the analyzing magnet, which rotates and is able to fit each of these beam lines. And I will try to describe very fast in this order. So starting from this at the top, the radiation damage on semiconductors line. This is mainly used for space application in order to simulate the cosmic rays, which impacts on solar panels. They have here in the middle of the line a wheel with attenuators which enlarge the irradiation area and reduce the flux, just to simulate as close as possible the space situation, the situation from cosmic rays. And they also have a cooling system with liquid nitrogen and heating to simulate the very fast change in temperature that occurs in space conditions. So they try to reproduce as well as possible those conditions, to test, of course, the durability of electronic chips and solar cells in satellites. There is also a micro beam line, which is used for pixel. This is a picture of this micro beam line with the quadrupole here, the triplet quadrupole, which make the final focusing. And here they will just plane and draw a map of Argentina within a millimeter. But the actual use of this micro machining is to build waveguides in lithium novate. Other applications are, for example, testing CMOS amplifiers. This red dots indicates where the beam was impacting in the moment this amplifier had a failure. So they can detect in this way which are the most sensitive components of this amplifier on a very small scale. Another use of this pixel is as an environmental tracer, or let's say to see which is the composition of a target or of a sample. They irradiate with this microbeam, which is have a spot in the order of the micron, and each chemical element has a characteristic X-ray, which is induced by the impact of the particle. And in that way, you can identify those elements. It's being done with oxygen ions, which give much more sensitivity than usual protons, which are usually used in this kind of experiment. One of those of the application for this microbeam is to map how aquatic plants concentrate metals, in particular uranium, because these plants are very useful for bioremediation. Let's suppose in a hypothetical case that uranium is released in a lake or in some river. This plant can concentrate uranium and can be easily extracted from the lake or from the river. There is also, going in this direction with the beamlines, an external proton beam, which was used some years ago, actually 2 decades ago, for irradiating biological cells. Actually, my wife, who is a biologist, did this experiment for her PhD, well, 2 decades ago. One of the disadvantages of having such an external horizontal beam is that the cell culture well was have to be put it in this vertical direction, so it could not hold the liquid medium in which the biological cells like to live in. So, well, she told me it would be much better if we can get a vertical beam. So an idea is, which is still not being done, it's just planned, is to use just the machine is vertical, so we can use the vertical beam before the analyzing magnet. This is the analyzing magnet. So there is an outlet for the beam here in the back part of the analyzing magnet. So with that vertical beam, you can place the cell culture well in horizontal, in normal position, and holding the liquid medium. So this will, or it's expected to make this survival of the cells much more reliable, just to be sure that if the cells are killed by the radiation and not because they were without liquid. So this is still not being done, but it's planned for some future. So moving on with the lines, we have here an AMS line, a line built or rebuilt actually for accelerator mass spectrometry, in which we included a beam filter. This is a layout of this rebuilt beam line. We included this beam velocity filter. One detail is that our machine is vertical, so the analyzing magnet selects in the vertical direction. And since we have no switching magnet, was better for us to have the beam filter selection in the horizontal direction in order to decouple from the selection from the analyzing magnet, to have in 2 different directions. So we have to redesign this beam filter to be in horizontal position. So it's working in like this, the electric field in the horizontal. And after the beam velocity filter, we have almost 7 meters time of flight with a start and a stop and a quadrupole in the middle. This is how it looks like. This is the beam filter, and this is the start, and this is the stop detector. This is a close-up from our nice beam filter. And this is a picture of the microchannel plate detector, the one which makes the start signal for the time of flight. These are some results for uranium-236. You know, the usual isotope from uranium are 35 and 38, and 36 is being built by, well, 18% of the captures from uranium-235 does not go to fission, but they remain as a compound nucleus 236, which is a radioisotope. It has a mean life of a half-life of 23 million years. So on the one side, it's a signature that tells you that some element from uranium has been used or not in a reactor. If it's virgin material or not has been already used. And on the other side is a very sensitive for environmental studies. Let's say that it's very rare in nature unless there is a huge contamination. So it's a very sensitive tracer for contamination. So here is how we could detect the 236 with the time of flight spectrum. Another application that we performed at the Tandem Accelerator was the measurement of another radioisotope, beryllium-10. Beryllium-10 is very useful for geology because of its mean life, which is, well, the half-life. The half-life is 1.4 million years. So it fits very well the geological processes. This is usually measured in small machines, but the advantage of using a large one like our facility at 8 megavolts is that we can completely suppress the boron-10. Note that boron-10 is an isobar, has exactly the same mass. It could be difficult to separate it. So when you have high energy or high enough energy, you can use a passive absorber in order to completely stop boron-10, which have 5 protons, and let beryllium-10 goes into the detector. This is how the detector looks like in reality. This is the passive absorber, an argon gas cell, and the detector itself. And there goes both beams. These are our spectra, which are free of boron. We have no boron in the spectra. This allowed us to study some marine sediment samples in order to assess some some geological process of subduction of tectonic plates. So let's go now to, well, we have also a magnetic spectrograph, which is quadruple and 2 dipoles. We also have here the beam light we use for nuclear reaction studies, for basic studies. Among the most important feature of this line is this reaction chamber or target chamber, which have 2 rotating platform or plates here. This is the one on the bottom, and there is another on the lid of the chamber. So we have 2 places to place detectors. This is computer controlled with quite good precision for the angle. We have typically 2 monitors at the side and a Faraday cap. This is well, now we were using an array of 8 silicon detectors, and this is our target, and this is how the beam goes through. With this system, we were able to study, for example, the elastic scattering and also inelastic one. Here is the lithium-6 plus selenium, in which we could detect, well, of course, the elastic scattering, and here there's an excited state. And there is also lithium-7 being studied. This was studied with Sao Paulo potential and also with the Wood-Saxon phenomenological optical model. One of the features we studied from these 2 systems was the so-called threshold anomaly, in which the parameters of this potential vary with the energy when you get close to the Coulomb barrier. So for instance, here in the lithium-6 case, you see there is a signature of the so-called breakup threshold anomaly, in which there is an increase of the imaginary part of the potential before it definitively closes. So you have this increase and then the decrease when you go to lower energies below the Coulomb barrier. For instance, for the system lithium-7, the signature was from the ordinary threshold anomaly. We also start beryllium-9 over selenium, and what I wanted to comment on some detail is that there is some arbitrary choose of this fitting here. Let's say the usual procedure is to fit with a linear function the imaginary potential, and then to integrate, to calculate according to the dispersion relation how it's supposed to be the real part. So when we study the beryllium-9 over selenium, we try to develop some procedure to do it more systematic way. These are the points that we were obtaining for each energy, for the imaginary part. Then you can calculate the uncertainty in each one of these points. You can, let's say, this uncertainty can be done with two methods. One is the chi-square criterion, let's say, to let the chi-square increase up to this other quantity, this other value. Usually, sometimes they use chi-square plus 1, but when you have two variables, it should be in this way. And the other method we tried, and it works quite well, although it might be time-consuming, is to use bootstrap. Bootstrap is a method in which you select some set of measurements. Let's say that you have 50 angles or 30 angles, whatever. So you make subset of 30 selected angles from the angular distribution, and each of these points correspond to the calculated value using this bootstrap method. So either using bootstrap or this chi-square criterion, you can calculate several points for each of these, and this is called Viva rate random sampling. For each one, there is a different fitting for the imaginary potential, and for each of those, you can calculate an independent real potential. So in that way, it's much more robust, we think, when you say that the signature is of the breakup threshold anomaly in this case. Another system which was very recently studied is beryllium-10 plus gold. Let's say that we are getting, well, this has a quite higher Coulomb barrier, and this is can be done with a large machine. We studied, of course, the elastic scattering, and we got two inelastic, two excitations. Actually, they are, for the case of gold, these are not individualized as a single state, because here we actually have 3 states, and here we also have 3 states. So these are not individual states, but the contribution of 3 in each case, at least 3. Once again, we apply this methodology and got this signature for the threshold anomaly, which once again seemed to to indicate a breakup threshold anomaly. Another system which was analyzed by our friends from Spain, by Manuela, Jesus Casal, and Jose Maria Arias in Seville. They analyzed this data using 4 bodies continuum discretized coupled channel, and this was commented, I think, a month ago by Manuela herself when she gave her talk. We also have some states which are in elastic state, elastic scattering, which are quite well individualized for the case of TIN 120. Moving on to other kind of detector, we also have some telescope. We usually can mount telescopes to have a particle identification. One experiment being done in collaboration also with people from Brazil was done in 2019, before the pandemic, of course, and was to study the disappearance of Mott oscillation. Mott oscillations are those that you get in identical particle system we choose, or this was proposed by Valdir Guimaraes from the University of Sao Paulo. So according to the spin of the particles and for different Sommerfeld parameter, this oscillation may disappear, and the zero of the second derivative, let's say this blue curve here has an almost zero. It's very sensitive test for the nuclear potential model. So this is this distribution, which of course should be symmetric around 90 degrees. Another system that we are now analyzing, or let's say the experiment were fortunately done before the pandemic, and we are now analyzing the data, is deuterium over gold. Although it might seem quite simple, deuterium as a projectile, it has many output channels. Of course, the elastic scattering leading to deuterium itself, for sure. But then we have the breakup, which gives us some, let's say, low energy protons generated by the breakup. Then we have the neutron stripping. Let's say that we generate the high energy proton because we have a quite positive Q value, and on the other side we generate gold 198. We have almost 3 days of half-life, so it's also easy to detect. And another possible outcome is neutron pickup, which gives us tritium, and on the other hand, gold 196 with a negative Q value. So for these 4 different possible particles coming out, we mounted a 4-fold or 3-fold, as you wish, telescope. So breakup protons and tritium are mainly detected with the first 2 detectors, or the first telescope, if you want. The deuteron, the elastic scattering, you need 3 detectors, and for the more energetic protons coming from the stripping process. Remember that you have a positive Q value when transferring a neutron to the gold. You need the 4 detectors to stop this proton with these high energy protons. So this is how a typical spectrum looks like. Well, always that you say a typical spectrum, that means it's the best you have. This is the very nice spectrum that we got. Here at the top, the beam was 16 MeV, and here at the top we have almost 20 MeV, because it's basically this beam energy plus 4 MeV from the Q value going to the ground state of the gold 198. Then we have excitation from this gold residual nucleus. Then we have another processes generating protons. And here in this zone is the breakup bump. So for instance, this sharp peak was identified as proton contamination in the target. So these are knock-on protons which are knock-on by the deuterium projectile and coming into the detector. So this is just a contamination, this sharp peak. But this bump is indeed, or was identified with the breakup. So we are trying now to make an angular distribution of this breakup and compare it to what it can be calculated with the Fresco code. And well, these peaks on the right side are also contamination from carbon and oxygen. But the important part for us is this breakup bump. This is one angular distribution for 11 MeV. We have 7 energies measured in this system. As I said, when you generate the neutron stripping or neutron pickup, you of course produce the proton and the triton, but on the other side you also have the gold 198 and the gold 196, and you can detect offline both of them. This is how this neutron stripping and neutron pickup looks like, but measured from the offline detection of the target. After irradiating the target, we take it to a gamma detector and we can look at the production of both gold isotopes. This is another kind of detection. Let's say that these solid-state telescopes are useful for light ions, but if you have, well, heavy projectiles, you can not use a solid telescope because they won't go through the delta E. So this is an ionization chamber. We have, of course, a very thin entrance window. Had 2 sections for having delta E1, delta E2, and 3 position sensitive detector. And this gives us, in a 30 degrees range, the angular distribution in an almost continuous range of 30 degrees, but also particle identification. This detector was used, for instance, to analyze the production of alpha particles coming from lithium-7 plus samarium 144. We were able to measure the angular distribution of alpha particles, let's say separating alpha particles from lithium itself and protons and deuterons. This was measured, this non-capture breakup was measured with another system, with an exclusive measurement from 2 telescopes. So we could calculate the non-capture breakup. This part was, of course, this was doing inclusive measurements. That means measuring all alphas coming into the detector. So one part of this alpha was explained by non-capture breakup from the system, from this projectile, and the other component was complete fusion and alpha evaporation. So we were able to more or less describe what was going on from what the spectrum being detected with this device. Another technique or device that we have used in the past, now this was dismounted because we use the same thing for AMS, so we dismounted this time of flight, but it can be remounted if we want to or we need to, was to have a rotatable time of flight. Let's say this is a time of flight built on a rotating arm, profiting the rotating platform of the spectrograph. So in that way, we could analyze the time of flight at different angles, mainly forward angles, coming from this scattering chamber. In that way, you can identify fusion products in this time of flight versus energy spectra. Another kind of detector we are now testing and using is the double-sided silicon detector. It is mainly intended for the detection in coincidence, for instance, of alpha and deuteron. Let's say that we have lithium-6 beam breaking up in front of the gold and going into a backward direction, and we are interested in detecting in coincidence the deuterium and the alpha. This is how it looks like. Actually, you are seeing here is just a mylar foil, but the beam is coming from behind, going through this hole, impinging on the target and going back. This is how the naked detector looks like. It has 48 rings and 16 angular sector, or we call it pizza sectors. We have electronic for 64 channels. Maybe in some future, our friends from Brazil can come to us and bring some more electronic and some more detectors, and mount this with much more capability. But at the moment, we are having 64 channels, electronic channels, and this is how we have actually. We have two of these double-sided silicon detector, one which is 100 microns width, which acts as a delta E, and a residual energy which have 1000, and this can be used as a telescope. Of course, we can identify several particles. Here you can see the formation of lithium-7 from a neutron pickup process. This is a spectrum in which we compare the energy signal from one sector and a not adjacent sector. Let's say sector 1 and sector 5 from the angular sector. So what you're seeing here are deuterons and alpha on one side and on the other. But if we take instead adjacent sectors, it's much more clear. So here we can identify, I call them deuterium minus and deuterium plus, whether the breakup is going in the forward direction or in the backward direction with respect to the lithium-6 velocity. So you can identify this as the deuterium going backwards, this as the deuterium going forward, and the same with alphas. This can also be seen in one-dimensional mode or one-dimensional spectrum. The blue is experimental, and the red line is a kinematic calculation, just three-body kinematics. And the conclusion of what we can learn from this fitting is that this is supposed to be a resonant breakup because what was assumed was a 712 kV from breakup energy, would come from the excited state of the lithium-6, which there is a 3 plus at 200, almost 200, 2200 kV, minus the breakup energy. So this gives you this amount of energy. Well, I didn't include it here, but if you change this amount of energy a little bit could be 100 kV, you're already going to notice that this fit is not good anymore. So with a reasonable degree of reliability, you may say that this energy distribution of both deuterium and alphas indicates that the breakup went through this resonance state at this energy, 2000 kV. So now I may go to the offline method, in which maybe I can try to describe it with a little bit more detail. This offline method, actually we irradiate the sample. We have this very, very useful small chamber in which we can put the targets inside and take them away without breaking, without losing the vacuum in the whole chamber. That allows us to change the target in few minutes, let's say 5-10 minutes. We can change the target and be again with the beam on target. Then taking it to the gamma detector. Here you can see the lead shielding for the detector, and we studied boron and beryllium-9 over gold. And let me describe this two experiment with some detail. I will try to fit in time. This boron-10 plus gold was performed in a collaboration with our friends from the University of Sao Paulo and the University of Seville in Spain, in the so-called Peladona collaboration. Peladona, of course, stands for Pelé plus Maradona playing together. So in this collaboration, we measure this kind of spectra in which we can identify polonium, bismuth, lead, thallium, gold as well. A lot of stuff here, and it's easier to see it in this way to understand why we got so many things in the spectra. So we start with the gold as a target. We fuse a boron-10, go up to polonium-207 as a compound nucleus, which evaporate 3, 4, or 5 neutrons, feeding the isotope of polonium. This polonium, well, may beta decays, feeding bismuth, or maybe alpha decay as well, feeding directly lead isotopes. So we detect all of these isotopes being depicted here, but for instance, the amount of bismuth here was, let me say, larger than the one we could explain as the beta decay from polonium. So we may say that we have a non-zero contribution of this process. The evaporation of 3NP has a non-zero cross-section. We measure a cross-section for the 3NP, and this one, on the contrary, written in white, are compatible with zero. Let's say that the amount of bismuth we measure here is compatible with the amount of polonium, the beta decayed into it. So we cannot say that we measure this process. Maybe it exists, maybe not. It's compatible with zero. So those in black are non-zero processes, and those in white are compatible with zero. We also have here proton stripping and proton pickup, and this process was actually measured online. This was measured in Sao Paulo. We at Tandem in Buenos Aires in Argentina, we measure this offline, and the online was measured at the University of Sao Paulo by our colleagues. So this is how these 3, 4, and 5N looks like, the excitation functions. These are the alpha 2N evaporation and the NP and 2NP and 3NP evaporation. And this is pickup and stripping, and this is quite remarkable, at least for me. We measure, as I said, the offline here at Tandem, detecting the gamma ray coming from gold 196, and the stripping measuring the gamma ray from 198 mercury. Sorry, here should say gold as well. But our colleagues in Sao Paulo, they measure online, the online detection of boron 11. So these yellow dots are a different laboratory and a different method. One is offline, and the other, in one case we are looking at the gammas, and the other case they are looking at the boron 11, and they fit quite well with each other. So that was at least, I don't know, a relief that things seems quite consistent, at least. Well, this is how the total fusion looks like. We have some enhancement here below the barrier, and this is a comparison with a lot of several systems. The black dots are our data from boron 10. This is the other system, beryllium 9, which also was studied by a group from India and also a group from China. We have a collaboration here with people from Rio in Brazil, from this university in Brazil. And of course, we have no polonium here. We go up to bismuth. This is the same chart for explaining this system. We go up to bismuth 206, evaporate 3, 4, and 5 neutrons. This is a comparison of our data with that of those from Kaushik. I don't know where Professor Kaushik is in the audience, but this is also data from Li, from a Chinese group. This is some phase calculation, which I try to do my best, but I must thank Vijay, who helped me with this calculation. We mostly agree here in the cross sections. For the foreign channels, we lie somehow below. We are below those data from Kaushik and from Li. We are somehow below. In 5N, we are quite in agreement with the Chinese group from Li. Then we have this, we have two contributions here, the complete fusion going to thallium 200 and the incomplete fusion. The phase calculation or the calculation results are 2 orders of magnitude below what we measure. So that's why we think that the incomplete fusion should do the most part of the work here. I try to fit or calculate with phase, trying to describe, saying to phase that I have an alpha beam. That's not true. I have a beryllium-9 beam. So I was able to reproduce this part, low energy part, but not here at the high energy. That was only to play with, not to be taken seriously. Also the thallium 199, let's say the evaporation of alpha 3N, is also quite much higher than what phase code calculates for the complete fusion. And here is the neutron stripping, and this is quite noticeable that we measure the neutron stripping. That means the production of gold 198 down to energies of
Thank you, Professor Arazi, for a wonderful talk. It was very interesting to see so many results all together. So the session is now open for discussion, comments, remarks, if any. Anyone?
Hello.
You can
Yeah.
just unmute
Yeah.
yourself and ask. Yes. Yeah.
Yeah. Myself, VK Naik from Mumbai.
Mm-hmm.
Yeah. So I have a couple of questions. First question is on Pixie.
Yeah.
Where you told that you are using oxygen beam,
Yeah.
right?
Yeah. I'm not. Yeah. Yeah, please.
I'm just wondering if you are using oxygen, then must be multiple ionization. So how you are taking care of that? Because the X-ray line, when you detect, you will get multiple, lines.
Yeah.
It will split.
Yeah. What they told me, because I'm not working in that area in Pixel, but that with oxygen beam they have much more sensitivity for heavy elements such as uranium that they are looking for, or they are interested in. So there is a so-called L lines. For those lines, there is much more sensitivity using oxygen beams rather than protons.
Okay. I have another quick question. So
yeah, please.
Because we are trying to study this weakly bound nuclei. Why not we take one target and then you take a series of suppose like lithium 6, 7, lithium 8, like this one series you take, and then whether that will give a better physics understanding.
Maybe I can get the idea at the end, but so you say you have lithium. You are proposing doing lithium 6, 7, or
7, 8, whatever available. 11.
One important thing I forgot to say is that we don't have radioactive ion beams.
Okay.
But our colleagues in Sao Paulo, they do have. So this is a very nice complementation between. They have, let's say, this facility for doing radioactive ion beams, and we have a little more energy at our facility, so we complement each other very good.
Right.
So, but if you have some proposal for, let's say, lithium 8, they can for sure do it in Sao Paulo, in Brazil.
Yeah.
So that could be a very nice 3-part or 4-part collaboration.
Yeah. Okay. Thank you.
Yeah, you're
Thank
welcome.
you for your nice talk. I enjoyed your talk.
Thank you.
You speak very nicely, slowly, and also
okay.
You explain things. It was really enjoyable. Thank you. Thank you so much.
Thank you very much.
So we can have next question now.
Hello.
Yes.
Hello, am I audible?
Yeah. Yes, we can hear you. Yes.
Hi, Professor Arazi. I would like to repeat what Professor Naik said. You are really a very wonderful speaker. I couldn't stop myself from saying this. I am Deepika Chaudhary. I work at Indian Institute of Technology in Punjab. I have a very small question regarding the detector that you showed, the delta E detector. You showed like E1, E2, E3, E4. There are 4 parts. And you showed that it's an ionization chamber, like E1 and E2. Am I right?
Yeah.
So what
should I put the slide back in order to?
Yeah, please, if you can.
So you were referring to this one, for instance?
Yes, this one.
Yeah.
So
here, please.
This is like E1 and E2. These are the ionization chamber with different weights, right? So what is E3 and E4?
No.
Or I
Sorry.
understood wrongly.
Maybe no. These are two different. I put them together one after the other. But this is one detector, and you have delta E1, delta E2, and let's say residual energy, or call it delta E3, given by the solid silicon detector.
So these are silicon detectors.
Yeah. Which, on the other hand, gives you the position. So we have, let's say, three stages: delta 1, delta 2, and residual energy. And on the other hand, we have the incidence position, or let's say the angle. The advantage of this detector is that we have, with just 8 signals in total, because we have 2 signals from each detector. No, we have 6, and the 2 ionization chamber signal, we have just 8 the signal. We got the complete angular distribution plus identification. That was thought in some time that we just have an 8 channels ADC, and we didn't have 2 ADCs to use, so we try to fit as much as information as possible with just 8 signals. Now we have this double-sided silicon detector, which have, of course, much more signals and much more information. But this is still useful for heavy projectiles. And the other detector, this is another thing. This is just 4 regular silicon detector, transmission detector, put together. Let's say we just join 4 the transmission detector, because in the case of the deuterium product, we have a product with very different ranges. Let's say that the tritium is going to stop very soon in the 2 first detectors, and these very high energy protons need much more silicon to stop it. So
okay, understood. Thank you very much.
Yeah, you're welcome.
Any other questions?
Hello, am I audible?
Yes.
Yes.
Hello, sir. It's a very nice talk, and I'm
Thank you.
Malika Kaushik from IIT Ropar.
Oh, okay. Yeah. Okay, you're very glad to meet you.
Same here, and it's a very informative talk. Thanks for presenting such a nice work. And I would want to ask some question on neutron stripping. In one of your slides of neutron stripping, there you have shown CRC calculations.
Neutrons in beryllium 9, no?
Yes.
Here.
Yes, this one. So these red solid circles are the experimental data from your group, right?
Yeah. For sure. Sorry. Yeah. These are our data. Yeah.
Yes, sir. And maybe I have missed. You have used this offline technique also, right?
Just this offline. We have no other. We have not detected online beryllium 8.
Right.
We just use the gamma emission from gold.
Right. So you have shown here the CRC calculation, right? So could you please comment that this, what do you mean by more important states of 198 gold and up to 703 keV? Could you please comment over this? What do you mean?
The more important state, that it's maybe with I don't know if our theoretician in chief is in the talk. Maybe he can explain it better. But the idea is how many states were used in the coupled reaction channel calculation. There were just train using up to this energy of 700, then
Right, sir.
from 700 on, you have plenty of states.
True. Because there are huge number of states in 198 gold,
Exactly.
right?
Yeah.
Right.
So yeah.
Yeah. So I would like to ask that how do you say that this is the more important states? Is there any particular criteria, or you have done some specific calculations to point out that these are the important state, and why you take states up to 703 kV? Is there anything means firm reason behind it, or it's just mere calculation?
I guess that I'm not the one doing those calculations, but
Okay.
I think that there is a trade-off between the capability of calculating and the weight that they have. Actually, what they try to check is that including more, they're not bringing significant increase in the cross section. So they try to check if there is some convergence, including one more or one less of those states. But there is a plot in, maybe I can look, in which they show how many states they took in account, which are plenty of them. Maybe
Right.
I can show you the.
That's completely fine. If you don't
if I find the paper right as we speak, oh, there it is. Are you able to see
Yes,
my
yes.
screen?
Yes.
So here they plotted all the states being coupled in gold 198, which are plenty of them.
Right.
But maybe if some of the theoretician collaborators can clarify you much better than myself.
Yeah, it's completely fine.
Why they choose this one and not the next one and not the, I don't know.
Right. So because I just want to point out that here you have used two states of 8 beryllium, like ground state and first resonance state, right? But for 198 gold, you have chosen some of the low-lying states, right? There are huge number of low-lying state in 198 spectra. So for this also we have to choose, rather we have to choose completely randomly, or we have to choose some trick that which states are giving more contribution to the cross section. Maybe there are some different techniques, so you have to choose like that. And these 198 states are up to 1.156 MeV states. So you have retained up to 0.7, right? But I have seen.
Yeah, exactly.
Yes.
Yeah, exactly. Yeah.
So I just want to know that it's good to see this that you have chosen, and because in your experimental data also you have gone up to much below the barrier, but I have seen up to 20 MeV, right?
Yeah.
So,
yeah. But sorry, 20 MeV just for the neutron stripping. For let's say fusion evaporation down to 32 or 33, not less than that. But our surprise was that we could go further and further down in energy, down to 22 MeV, and we were still seeing some neutron stripping.
Right, because offline technique is more beneficial to point to below barrier cross sections. It's cleaner technique, so we can go much below barrier. So this is my point, that even if you match your cross section at above barrier, like we have seen in your presentation, but below barrier still there is a lot of discrepancy in this cross section of theoretical and measured cross section. there is a huge difference between theoretical and experimental cross section here. Yes.
Here, yeah, for sure. That's why we say, that this is, let's say, for us, when we did the experiment, we were expecting this neutron stripping to go just like any other channel to close below barrier. But we've got this low energy tail, let's call it tail. So, as you say, when you calculate, the theoretical calculation goes downwards. So what we guess, and that is just a guess, is that the breakup is doing this contribution. That the contribution is being done by breakup. So I don't know if Professor Lubian is hearing now, but he will certainly say, "Don't say that, don't say that." But I can avoid it, and these are two
yes, there is a probability that it may there is a contribution from breakup also here.
Yeah,
so that's why there is a huge increment in the transfer cross section.
Exactly. So the red dots and the blue curve are different processes. Something different. One is production of 190N, and the other is breakup of the beryllium-9. So saying that these are the same is assuming that all neutrons having produced by the breakup are all going to be captured by the goal target.
Right.
Can be weird, but I mean, what the only thing we can say is that there is some coincidence between this measurement and this calculation. That's all what we can.
Yes, because we cannot distinguish between these two processes in our technique.
No,
right. That's why we can say that these are the contribution from both of the processes. We are
exactly.
We are not sure that from which it is populated.
So it's a huge temptation to sum up this red curve with this blue curve and try to fit the data. Maybe it fits perfectly well, but let's say we have no evidence to sum these things up because they are different things.
Right.
That's the idea.
So blue dashed line is sigma breakup. What is this? What is this? This sigma breakup is is calculated one, or these are the experimental, because you have written it sigma breakup, and this blue dashed line, blue dotted line, yes, so which matches at below barrier is this is your calculations from the same code. Is this?
Yeah.
And so you have used the CRC code also here for this breakup part also.
Sorry.
So for calculating this sigma breakup, you have used the same code.
Oh yeah. The Fresco code.
Okay, so these are the mere calculations for breakup, right?
Yeah.
So okay, so the other part of the same experiment which you are talked of, like fusion and thallium cross sections, are they published one, or they are still in process, like you have shown in one of your slides?
It is submitted, and we are waiting.
Okay. And so have you done the breakup theoretical calculations also for this?
Well, but I didn't do myself, but I don't know. I'm not seeing.
No, I'm just curious about that.
And can I interrupt you?
Yeah. Please. Here.
You can go back to the slide.
Yeah, our theoretician come in my rescue.
No, not so much.
Yeah, please go ahead, Barbara.
We perform here CRC calculation with a polarization potential calculated by CDCC calculation to take in account the breakup. This blue dotted line is CDCC calculation. We give you the elastic breakup.
Yes, yes. This is what I'm
And
asking. That
and I know that you asked these more important states. We are not allowed to put every state the gold 198 have, because have a lot of states. But these more important states is related to the more cross section that we obtain up to 703 keV. We go up to these states and analyze the more important inside these states. We not put more states than this.
Can I make a question on this topic to Barbara?
Yes, Leandro.
You said that you have done CDCC calculations, right? But you have done a 3-body calculation?
Yes.
Or 4-body calculation?
No, a 3-body.
3-body. So it's
gold is perform a 4-body.
Yeah, but then it's helium 5 plus helium 4. The partition that you consider. How do you describe
this is beryllium? It's boron 8 plus beryllium 8 plus a neutron.
So it's beryllium 8 plus neutron. Okay, yes. Okay. And Andres, are you planning to measure the 2 alphas in coincidence in this case? Could you do it?
Yeah, for sure we can do it. Yeah. Actually, we did it. I mean, we have some spectra already done with these strip detectors.
Yeah.
I don't have it right now, but if in the spectrum I show there is alpha coincidence, where it is. There is some place.
Yeah, this is for lithium 6, right?
Yeah, for lithium 6, but these ones are alpha. When we use a beryllium 9 beam, this region was quite full. Let's say this was the most important region, which was the alpha alpha coincidence. Yeah, for sure.
Yeah, good. That might be a good signature of this process. Very
yeah,
nice.
Exactly. In this case, in case of lithium, you also get some alpha, but it's much less than the deuterium alpha. But for sure, and actually one of the plans was to study this beryllium 9 over tin or over gold, and study in coincidence this coincidence detection of the breakout products.
Very nice. Maybe you can talk later.
Yeah, for sure. So as I said, the idea is that as soon as this pandemic goes away, we can return to let's say to our usual collaboration, and we are open to any proposal, and we are welcome for sure.
Okay, very nice. Good.
Thank you, sir. Thank you for clearing doubts. Thanks a lot.
Thank you.
Okay.
Yeah,
yes. Yeah, Vijay, please.
Yeah, Bhumika, can I?
Yes, sure.
Okay. Thank you very much, Professor Andres, for sharing such a nice facility in Argentina, especially for nuclear reactions.
Yeah,
I wonder if you have the particle gamma coincidence set up there.
Yeah, I am. Well, sorry, it's not gamma particle coincidence. It's just we have gamma detection, and on the other hand, particle detection. We are planning to do some gamma particle coincidence, but we haven't done it yet, and of course there is no such a picture now. I mean, we have these are, for instance,
the particle-to-particle coincidence.
This is particle, yeah. With this detector, with this strip detectors, this one, they are just particle, and on the other hand, we did offline detection of gammas, and we are planning, not yet done, to have, let's say, 2 gamma detectors in coincidence to get rid of most of the background, but haven't done yet.
All right. Yeah. So once I be there with you, so we can just develop this particle gamma coincidence setup. Because
sure.
I'm so much interested to understand more about the angular momentum associated with the breakup particles, evaporation residues which formed, populated by the breakup and formed by the complete fusion. So that's my idea.
For sure.
Yeah.
For sure. Yeah.
Yes. Thank you very much.
Thank you.
Is there any other question or comment? If not, okay.
Andres,
yes, please.
Yeah, only a comment. Nice to see the development at the Tanda laboratory, that you all come up with this delta E setup as well. The one which we worked was with only E during the yeah. So it's nice to see the facility for the coincidence measurements and for the that one. Yeah. The one AMS you were working at, you're starting to work at that phase when I was there. So it's nice to see that you carry forward so much amount of work. Yeah.
So Nikit has been at our facility, and in that time we measure boron 10 and boron 11 over nickel. Over nickel.
Yeah.
And we were quite lucky that everything went quite well. We have 3 weeks of big time and almost non-stop, and we were quite lucky.
Yes.
We are not always so. So maybe you got a too good impression from us. It's not always so.
Yeah. A too good impression from the machine side as well as from your group side. It's always a collaborative, hard-working group, and is always ready to share the load in a very sophisticated way. Yeah.
So I hope to host you back soon.
For sure. So give my regards to Bianca and Dante.
Thank you.
They're grown-up kids.
Yeah, for sure. Thank you.
Okay.
You are still. You have one daughter, or?
Yeah, no, one daughter.
You went further.
No, I'm still
not yet.
To one. Yeah.
Okay. If there are no more questions, can I ask a small doubt? Means I'm not an experimentalist and I don't know about reactions much, but I wanted to know, is it possible to extract the spectroscopic factor information from using your facility?
Yeah. To get some spectroscopic
factor.
Yeah, you can measure the cross section.
Yes.
From there on, you can derive this spectroscopic factor. Yeah, for sure. But that kind of duty, I leave it from theoreticians. I just get up to the cross section.
Yes. I understand. Okay. It was really nice to have